happy today to have Lorenzo Ciardo speaking on where is the center of a graph.
Thank you. Hi everybody, and thanks for being here. The aim of this talk will be to try to give one possible answer to a very basic question, which is how to find the center of a graph. And marginally, we'll also be interested in how to find it in a computationally efficient way. So let me just say that whenever we have a graph modeling a network, let's say a telecommunication network or the map of roads in a region or something like this, it's often quite important, quite interesting to find the vertex or the set of vertices, the small set of vertices, which are best suited for some reason to control the rest of the network. This is what we are going to do. So, well, first of all, we see that for some very simple graphs, whenever there is some kind of clear symmetry in them, it's quite intuitive to understand where the center should be. So whenever we have a path with an even number of vertices, we see that the center should be the two vertices in the middle. For a path with an odd number of vertices, it should be just one vertex in the middle. For this other graph with a clear symmetry, we see that intuitively the center should be this one. But even for this other very simple graph, it's a tree, we see that there is some ambiguity, right? So we really need a mathematical background. And well, the classical way, one of the classical ways in which the center can be defined is by using the eccentricity of the vertices. So let's say that G is a connected graph. Given each vertex, we can define its eccentricity as the maximum distance of other vertices from it. And then we can define the eccentricity center, EC, of the graph as the set of vertices minimizing this maximum distance. So it's a kind of minimum of the maximum in some way. And well, let's test this center on our example. So, well, for the path, we see that the eccentricity here, it's 5, right? Because in 5 steps, we can reach all the other vertices. Here it's 4, 3, then 3 again, 4 and 5. So our intuition was correct, or at least it agreed with this definition. For this other vertex, this other graph, we see that from the central vertex, this here, we can reach all the others in one step. So again, our intuition was correct. And for this other graph, well, from this vertex here, we can reach all the others in 2 steps, and it's the only one attaining this minimum maximum distance. So the eccentricity center here, it's just one vertex. There is another notion which can be considered classical, the characteristic set. So here we restrict on trees, on n vertices, which we label from 1 to n. We can associate to this tree the Laplacian matrix. So it's the n times n matrix having the degrees of the vertices in the diagonal, and then -1 in position ij whenever I and j are connected by an edge, 0 if they're not. This matrix is not invertible, but suppose that we choose a vertex I and we color it in green, then we can consider the submatrix of L obtained by removing the ith row and the ith column. This submatrix here turns out to be invertible, and we can consider its inverse, B of I. And you see from here that it has quite a nice structure. So it's, at least from here, but it's true in general, it's a block diagonal matrix. And every block M corresponds to a branch T of G minus I. So we have the whole tree G, we remove the green vertex, we end up with a forest. We consider the trees in this forest to be rooted, meaning that the vertex which was adjacent to the green vertex in blue would be the root of the single trees. And each one of these single rooted trees corresponds to a block in the matrix. So here you see the blocks next to these rooted branches. Also, you can see that all the entries in this matrix are integers and are either 0 or positive integers. This is not this is happening every time, because basically there is a nice combinatorial description of these entries. The ij entry in the bottom in one of these blocks, which is called bottleneck matrix, is the number of vertices in common in the path joining the root to I and the path joining the root to j. Question?
So are you saying that it's block diagonal for all graphs or just trees?
This is defined for trees. You can actually define it also for graphs, but then like you will have to care about blocks in the graph. So it's slightly different, and I want to use this notion just for trees because I'm interested not in central blocks of the graph, but in central vertices. So this is the difference. Okay, so we have this matrix here. Every block is called a bottleneck matrix, so the branch, and it is symmetric. It is entry-wise positive, so we can apply Perron-Frobenius theory. In particular, the spectral radius of the block is attained in one eigenvalue. It's called Perron value of the branch or of the block. A corresponding positive eigenvector is called a Perron vector, and it always exists and is unique up to scalar factor. And finally, a branch attaining the maximum Perron value at some vertex I is called a Perron branch. So in this case, we have 3 blocks, and the vertices the vertex attaining the maximum Perron value is this one. So this block here is the unique Perron branch. So one natural question is this Perron branch unique or not? And we have this classical theorem. The classical theorem is due to Fiedler, but this version is due to Kirkland. So given any tree G, there are just 2 possibilities. So the first possibility is that there exists exactly one vertex Z having more than 1 Perron branches. In this case, G is called a type 1 tree, and Z is called its characteristic vertex. And we can consider such a tree to be odd in some way. So there is just a unique vertex balancing in some way the Perron value. And if the tree is a path having an odd number of vertices, then the central vertex would be its characteristic vertex. Or, if this doesn't happen, there is exactly one edge, PQ, such that the unique Perron branch at P contains Q, and the unique Perron branch at Q contains P. And again, we can intuitively think about these trees to be even. G is said to be a type 2 tree in this case, and P and Q are called its characteristic vertices. Okay, so we see from this theorem that in all the cases, we can define a characteristic set of either 1 or 2 vertices, and we can consider this set to be a center. And now we can test this notion of our examples. So for this path, again, it has an even number of vertices, so it is a type 2 tree, and the characteristic vertices are exactly the ones our intuition told us, and are exactly the ones in the eccentricity center. So in this case, the 2 notions agree. In this case, this is not a tree, so we can't do anything from this definition. In this case, we had that both these vertices here are central, and this is a type 2 tree. So we see that this definition is not, does not always agree with the eccentricity center. Okay, but before continuing, I want to underline a kind of philosophical difference between these 2 center notions. To check whether a given vertex V lies in the eccentricity center of a graph, we basically need to compare its eccentricity with the eccentricity of any other vertex, right? We have to find the minimum. So we can think about the eccentricity center as a kind of global optimum. Well, to check whether a given vertex V lies in the characteristic set of a graph, of a tree, we actually only need to care about the vertices which are adjacent to it, right? So, well, we see it from this theorem here. Whenever we see that, for example, in the type 1 case, whenever we see that a vertex, one given vertex V has more than 1 Perron branches, then we already know that it is central. So this can be thought about to be a kind of local optimum. And at least again, like philosophically, intuitively, we can think that this second notion, can be more efficient. Okay, so the aim of the talk would be to try to extend this second notion of center, so this characteristic set, to general graphs. So to take it as a model for building a new center concept. Okay, and this is what we are going to do now. So we start with a general connected graph G on 8 vertices. We replace any undirected edge with a corresponding pair of directed edges, so arrows pointing in opposite directions. We call this directed graph G deer. And now we want to assign numbers to these arrows. So we choose a function, mu, from the set of arrows, so from the set of edges in this direct graph to R. Again, this just corresponds to drawing a real number on the arrows. And for now, this function mu is random. We can take the one we prefer. Then we will see that using some specific mu, we will get interesting results. And then we use this to build another graph, another directed graph called the optimality graph, G mu. So we start from the same vertex set of the graph. And then for each vertex V, we consider all the arrows having tail in V, so all the arrows which start in V, and we pick just the arrow having the biggest number of it, right? So we pick the arrow, the directed edge, which maximizes mu among all the directed edges in G deer having V as tail. But if this maximum is attained in more than one edge, instead of drawing all of them, we just draw a loop. So a loop VB. Okay, so we can see an example of this. So we start with the vertex set, and let's start, for example, in A. So we see that there are three arrows having A as tail, but AC is the one with the biggest number, right? Because it's 5. So we draw just AC. And then in B, we have -1, 0, -2. So 0 is the biggest. So we go to E. From C, we will go to B. From D, we have many choices, but the biggest one is to go to C, and so on. From G, we see that we have -1, 0, 0. So 0 and 0 are the two maximizers, so instead of drawing all of them, we just draw a loop. And then we finish in H. So we have this other directed graph, and we will use this to define the center. So we define the mu center of the graph G to be the set of all the directed cycles in this optimality graph G mu. So the cycles which are in red here. Okay, so now we can wonder why this complicated definition, and the point is that this definition actually captures the combinatorial sense of the theorem by Fiedler and Kirkland. So in other words, suppose that G is now a tree, and suppose that we choose mu, this function on the arrows, in a specific way. So mu is the Perron value, so the spectral radius, of the branch we obtain at I by removing I and taking the rooted subtree having root J. Right, so we start with the tree G, we select I, we remove it, we end up with a forest, and we save just the tree having J in its vertices. So if mu of ij is the Perron value of this tree, then the center, the mu center, Z mu of G, is exactly the characteristic set. So whenever we are in a tree and we choose mu in this way, we end up with that other definition. So we can think about the mu center really as a generalization of the characteristic set. Okay, we will just need another definition or two other definitions. So we defined the center, the mu center, to be a set of cycles. Now we define the support or the center to be the set of all the vertices which occur in at least one cycle, or the union of all these cycles, right? So in this example, we have that the center has cardinality 2, because there are 2 cycles, and the support has cardinality 5, because there are 5 central vertices. Okay, and well, for now, for a given graph and a given mu, we have that the center can be anything. It can be also all the vertices. So we at least would like to define some properties which we would like to be true for a center. So we say that a center is simple if its cardinality is 1. So if there is just one cycle in the center. And we say that it is quasi-simple if the graph induced in G by the support is connected, right? So we define the center, we define the support, which is the set of all the vertices in at least one of the cycles in the center. And then we consider the induced subgraph in the original graph induced by this support. If this is connected, then we say that the center is quasi-simple. So in this case, well, this center is not simple because there are two cycles. But if we consider the subgraph of G induced by the vertices B, C, D, E, and G, we see it better from here. Well, we see that it is connected, right? So this center is quasi-simple, even if it's not simple. Okay. Well, we can see that simplicity implies quasi-simpleness, right? Whenever a graph has a simple center, it means that the central cycle is unique. So in particular, the subgraph induced by the vertices in this cycle is connected. But the other way around doesn't always work. Okay, so well, even a simple center actually may consist of many vertices, right? Because if the cycle is very big, then we may end up with a very large center. But in case G is a tree, of course, a tree doesn't have cycles, so it means that the direct version of the tree has just two cycles. This means that any cycle in the center of a tree has either one or two vertices. And so we see that whenever we have a tree and whenever the center is simple, its cycle is either one or two vertices. And we can recognize this to be true for the characteristic set. Okay, so well, first some simple facts which are true for any tree, any graph G and any function mu. The center is always non-empty. Also, the directed cycles in the center are pairwise vertex disjoint, or in other words, whenever we have a direct circuit in the optimality graph, it's actually a directed cycle. And finally, we have that the center is simple precisely when the optimality graph G mu is connected. And to see all these things, we need a structure theorem for the optimality graph. So we have that the optimality graph G mu is always a disjoint union of pieces made like this. So directed unicyclic graphs. So graphs having one directed cycle and then all the other arrows pointing to this cycle. So from this structure theorem for the optimality graph, we can prove easily all these three properties.
So, sorry, is this for a fixed mu, or is this for the Perron value mu, or is this for any mu?
This is for any mu. Yeah. Okay, so well, let's ask ourselves, when is the mu center of a graph simple or quasi-simple, right? Because in some way we want to constrain the size of the center. Well, it turns out that it's important, this property, the path monotonicity. So we say that a function mu from a set of arrows to R is weakly path monotone if it's decreasing, weakly decreasing along a directed path. So if mu of ij is always less than or equal to mu of jk whenever we have edges ij and jk. And strongly path monotone is the same but with strict inequality. So yeah, we're saying that whenever we follow a directed path, the value of mu is decreasing. And it turns out that this is sufficient to have simplicity or quasi-simplicity. So if mu is strongly path monotone, then the center is always simple. and if mu is weakly path monotone, then the center is quasi-simple. Unluckily, this strong path monotonicity is a very strong property. So whenever G is connected and mu is strongly path monotone, then if G is a cycle, we could choose this cycle to be a directed infinite path in the graph, and then mu should be always strictly decreasing, which is a contradiction. So in other words, whenever G is connected and mu is strongly path monotone, then the graph G is a tree. So this is a very strong notion. The weak path monotonicity is less strong, so it just requires for the edges in a cycle to have the same mu value. Okay, but now I want to focus for a while on trees. So let T be the set of rooted trees. You can consider a weight W, which is a function taking a rooted tree and assigning to it a weight, a real number. It's really useful to think about the weight as like really a weight. So it's a function saying how heavy it is a rooted tree. And we have many examples of W. So it can be the number of vertices, it can be the maximum distance from the root, it can be the number of leaves, of pendant vertices. And here I want to point out that by convention, I want the number of leaves in a tree having just one vertex to be 1 instead of 0. Or it can be the Perron value. It's again, rho is a function taking a rooted tree and assigning to it a number. Or it can be a combinatorial Perron parameter, which is some kind of cheap approximation for the Perron value, which I will mention later. But again, so we have many examples of this weight. And whenever we have an unrooted tree G, we can use W to induce a new function, WG. So this function WG takes the set of arrows, so the set of directed edges in G dir, and assign to each arrow a real number in the following way. So it takes ij and it assigns to it the weight of the rooted connected component of the tree we obtain by removing I and saving the component having j as root. So again, we start from G, we remove I, there are many connected components, we save the one having j as root. That is a rooted tree, we compute its weight, so this would be WG of ij. And we notice that this definition here, it's exactly, this function here, WG, is exactly a mu function. So it's a function taking an arrow and assigning to it a real number. So it's a function that we like, and we can use it for free to define a W center of the graph. So we say that ZW of G, so this W center of G is ZWG of G, where this object here is the mu center. Okay, so we see from here that for free, whenever we have a weight on the set of rooted trees, we can define a center for any tree G. Let's see an example of how this works. So let's take this tree here, and let's let W be the number of leaves, the number of pendant vertices. So we want to put numbers on the arrows. So for example, for this arrow here, we see that the rooted connected component associated with this arrow is just one vertex, right? Because we have to remove A and save the component having B. So this rooted tree here has just one pendant vertex, so we assign 1 to this arrow. For this other arrow, we see that this is the rooted connected component. It has 5 pendant vertices, so we assign to this arrow the number 5. And we go on, so here we have 4. The blue vertex is always the root. So we have 4 pendant vertices, here we have 2, and so on. Okay, and then we end up with an assignation of weights, of numbers to the arrows, and then we can construct the optimality graph in this way. So for example, well, from B, we have just one arrow, so in the optimality graph, we draw it. From A, we have two, one is 4, one is 1, so we go to D, and so on. And it has just one cycle, so this means that the center will be exactly that cycle, and in particular we see that this center now is simple. We will see later that it's not always what happens for this kind of weight WL, but in this case we end up with a simple center. Okay, so again, also in this setting we can ask when the W center is simple or quasi-simple. Question? And here we will need a strict partial order on the set of rooted trees. So it's actually better to look at the picture instead of reading this. So whenever we have two rooted trees T1 and T2, we say that T1 extends T2. So this tree here extends this when T2 is a pendant appearance in T1, or more formally, whenever there exists another tree T3, such that T1 is obtained by taking T2 and T3 and joining the root of T2 in one vertex of T3, different from the root. But it should be quite clear from the picture. And then we say that a weight W is weakly extension monotone whenever it kind of accords with this strict partial order. So when we have that T1 extends T2, then the weight of T1 is bigger than or equal to the weight of T2, right? So this means that whenever we have a big tree and a smaller subtree, then the weight of the big tree is bigger than the weight of the small tree. So it kind of makes sense. Strong extension monotonicity is the same, just we want strict equality here. Okay, and whenever W satisfies these requirements, then the center is simple or quasi-simple. So whenever W is strongly extension monotone, then its W center is simple for any tree G. Whenever W is weakly extension monotone, then its W center is quasi-simple for any tree G. And this proposition seems very similar to the proposition regarding the mu center that we gave before, but actually there is a difference. So in this case, W does not depend on the graph, right? W is just a weight on the set of rooted trees. And also its extension monotonicity does not depend on the graph, right? It's defined here, and G is not coming into this definition. So this means that we can take a weight, we can verify if it's strongly extension monotone or weakly extension monotone, and if it is, then we can use it to say that any center on any graph G using the weight W is simple or quasi-simple. It's kind of nice because we don't have to verify it every time. Okay, so well, let's apply this proposition on the examples we saw before. So the Perron value is strongly extension monotone, right? The spectral radius of the submatrix, a square submatrix of a big matrix with only positive entries, is always strictly less than the spectral radius of the big matrix. This comes from interlacing theorem. The number of vertices is again strongly extension monotone, right? If we have a big tree, then it has more vertices than a smaller subtree, and also the maximum distance. So in all of these cases, W is strongly extension monotone, meaning that the center is simple. So for free, any center using one of these weights will be simple. And if W is the number of leaves, well, W is not strongly extension monotone, but it is weakly extension monotone. So a subtree of a given tree can never have more pendant vertices than the original tree. So in this case, ZW is quasi-simple. And also, quite funny thing is that whenever we take W to be the maximum distance function, then the W center we have is exactly the eccentricity center. And this is kind of surprising, at least to me, because the eccentricity center comes from a different optimization problem. But on trees, whenever we choose W to be this maximum distance, we actually have that the eccentricity center can also be obtained by this different optimization problem. Okay, so I mentioned before as examples of weight, the combinatorial parameters. I will not say much about them. I just say that they are computationally efficient approximations to the Perron value. So the Perron value is a spectral radius, so it's an eigenvalue. To compute it, we can use like fast algorithms, we can use QR algorithms, but still it will be more expensive than computing a combinatorial expression. So here we have defined some possibilities to approximate in a combinatorial way the Perron value. And one of them is called, we call it rho C of t. So it's the Rayleigh quotient computed in the distance vector d of the rooted tree t with respect to the bottleneck matrix m of the rooted tree, right? So it has this formula here, and well, the reason of it is that if instead of d we had the Perron vector of the bottleneck matrix, then we would obtain exactly the spectral radius. Right, the Rayleigh quotient in the eigenvector is exactly the eigenvalue. Here, instead of using the Perron vector, we use a distance vector, and for some reason the distance vector is a good approximation of the Perron vector. So we hope to end up with a good approximation of the Perron value. And it's actually the case. Okay, so again, this rho C is another weight we can use to define a center. Well, rho C of t is always a lower bound for rho t. This is a simple fact coming from the fact that rho is the biggest Rayleigh quotient, while rho C is just one specific Rayleigh quotient. Unluckily, it's not true that rho C is extension monotone, even if it took us quite a lot of time to understand it, to find a counterexample, and we found a counterexample of, an example of a tree having a non-simple center. This is the smallest example we know, so it's a tree having 135 vertices, having a non-simple and even not quasi-simple center. So it's kind of unfortunate. There are many ways, some ways to overcome this problem. The first one is not caring about it. So this center turns out to be simple in the vast majority of trees, and then we can say that for applications it's enough. Or a little bit more mathematically, we could say that this center is always simple for some specific classes of trees, for example for caterpillars. This comes from the fact that rho C is strongly extension monotone on rooted caterpillars. Well, we can take this rho C center. It's an operator, right? It acts on a graph, and it gives you a set of cycles. So we can take those cycles, we can take the subgraph of the original graph induced by the vertices in these cycles, and then we can iterate, right? And we will end up in the end with something simple. So in other words, we can define this limit center, which is obtained again by iterating this process, and this will be always simple. So for application, we can just use this. Okay, now we can finally compare all of these examples of center. So here I compare the distance among centers computed using different definitions. So here I'm using rho, so the Perron value. Here I'm using rho C. Here I'm using the number of vertices. Here I'm using the maximum distance, and here the number of pendant vertices. And these are computations made on randomly generated trees having 200 vertices, so quite large. We can see that the average distance is quite small, so it's never more than 1. In particular, here, so for rho and rho c, we see that the difference is 0.03. So it means that if we have one tree with 200 vertices and the rho c center is not equal to the rho center, but they are adjacent vertices, for example, then for other 32 trees with 200 vertices, we can expect that the two centers coincide, right? So they are very, very close. And here we compute the CPU time. These are quite basic algorithms which basically have been created by taking the definition on the paper and writing it on MATLAB, so I'm sure that there are better ways to implement them. But still, like, we can see that, at least if we consider the basic definition, there is a difference in CPU time. So the time to compute the rho center, which is the characteristic set, is quite significantly bigger as we increase the number of vertices than the CPU time to compute all the other centers. And this is because rho makes use of eigenvalues, so to compute them is more computationally expensive than to compute all the other functions which are combinatorial. This scale is logarithmic, by the way. Okay, so this means, so if we take this and we put it together, we can conclude that one way to see this notional center is that it gives close and computationally efficient approximations to the rho center, which is the characteristic set. So we can find something very similar to the characteristic set in less time, basically. But before concluding very soon, I want to say something about another way to define a center, or at least like another way to choose mu in the definition of the mu center. So here we again let G to be a generic graph, not a tree anymore. But we consider a very specific class of mu functions, which I call discrete differentials. So df. So let's consider a function f on the vertex set of the graph, right? A function f from V of G to R. Its discrete differential d of f is a function taking an arrow ij and assigning to it f of j minus f of I, right? So it's f in the end of the arrow minus f in the tail, and this is actually the way numerics people probably define the discrete differential, because if we take the limit of it, it's actually the differential. Okay, and then again for free, we have a function. We have a function going from the set of arrows to R. It's one of the functions we like. So for free we can define the f center of a graph G, zf of G, to be z df of G, with no like effort. So before going on with the last slide, I want to just point out an analog. What's happening in the continuous and what's happening in the discrete case. So in the discrete case, we have a function f from the vertex set of a graph to R. In the continuous case, we can think about this function to be function f tilde from Rm to R. Actually, we can think about it to be a function from any smooth manifold to R. It will be useful to think this f tilde to be smooth, or at least differentiable. Okay, a vertex I in G then corresponds to a point in Rm. An arrow ij in G dir would be an arrow starting at I and going in the direction of J. So it would be an element U in the tangent space of Rm at P, right? Yeah, it will live from P to some direction. But then, if we compute the discrete differential of f in ij, well, it's the value of f in j minus the value of f in I. If we consider the limit, this will be the directional derivative of f tilde in P in direction U. And now, like we can see that the fact that ij belongs to the optimality graph G df, well, it means that ij is the direction in which df is biggest as possible, right? But from the definition of df, we see that actually this means that ij is the direction of maximal increase of f. So in other words, u is the gradient of f tilde at p. And then if we consider the whole optimality graph, G df, it corresponds to the gradient map, gradient of f tilde. So the map taking any point and assigning to it the gradient vector. Okay, but then a cycle in the optimality graph, well, it's a bit harder to imagine now because in the continuous case we can shrink the cycle, in the discrete we cannot. But see, it corresponds to a point in which we are changing the direction of the gradient, so an attractor point in the gradient map. And if f tilde is smooth and nice, then it's a local maximum. Okay, but then the center, ZF, will be just the set of local maxima for f tilde. And finally, if ZF is simple, then there is just one cycle. So that there is just one local maximum for f tilde, and this is a strong indicator that if we want simplicity, actually we need to look at convexity or concavity actually, and this is what we will do. So we take a function f from the vertex set of a graph to R. We say that it is weakly concave if whenever we have a triplet of distinct vertices x, y, and z, such that y lies in some shortest path connecting x to z, whenever we have this, then f of y, f of the vertex in the middle, is more or equal to f of x times some weight plus f of z times some weight. And this is just the same definition of concavity in the continuous setting, just that the only difference is that here we may have more than one shortest path, right, in a graph. And we say that f is strongly concave when this inequality is strict. Okay, and then the theorem is almost exactly as we expect. We only need to require that G is triangle free, so in G there are no triangles. Then, given a function f from the vertex set of G to R, if f is strongly concave, then the center is simple. And if f is weakly concave, then the center is quasi-simple. So it's almost the same as in the continuous case. This triangle freeness is actually necessary. So let's consider this example of a graph clearly not triangle free. F is given by these numbers in blue, right? So f of A is 0, f of B is 2, and so on. So, well, in this case, to check the concavity, we only have to care about two different triplets. So, for example, if we consider A, B, and D, no one of these vertices lies inside a shortest path connecting the other two. So we only have to care about A, B, C, and A, B, C. And for these two triplets, this inequality holds, so F is strongly concave. But if we compute its center, so again we put numbers on the arrows, here we put 2 because it's F of B minus F of A, here minus 2 because it's F of A minus F of B, and so on. And then we draw the optimality graph, and we see that the center is not simple, and it's not even quasi-simple, right? Because the subgraph induced by A and C is not connected. So we really need triangle freeness. And that's all. Thank you for your attention.
Other questions?
Yeah. For your comparison, like a couple slides back, of all the different centers, how did you define distance between two different centers?
Yeah,
The minimum or the average, or?
that's a good point, and to write it like formally, it required me 1 page in the paper. So, but I can. So you are referring to
Right here.
here, yeah. So, well, whenever the two centers are made by just one vertex, it's just a normal distance. Whenever the two centers are both two vertices, I will take the middle point of each of them, and then we compute the distance. And whenever one is one vertex and one is two vertices, we take the middle point of the one with two vertices.
So it's the average pairwise distance between them.
Yeah, exactly, yeah.
And then you said here they're always less than 1. Can you prove that, or is it just on average always less than 1?
No, on average.
On average. So
actually, I'm quite sure that given any set of vertices, we can build a tree having that set of vertices as a center. Right? This is like not according to this, because this shows that the distance is always very small, but still there are some very like sick trees realizing any center. So at least this is true for the rho C center. For like the rho center, WV and WM, the center is always simple. So it's just 1 or 2 vertices.
So just sort of imagining a different kind of convexity question. So if you were to sort of smoothly transition from one weight function like mu to another weight function nu, have you studied at all like what happens to the center or the simplicity? I mean, it's clear that the optimality graph, like, you know, some things will get thrown in and then some things will get deleted, but nothing ever along that transition gets added back after it's been deleted. Have you studied whether properties like simplicity are sort of preserved along line segments?
No. One thing I noticed is that, like from here, for example, we see that at least for trees, the center doesn't seem to be actually dependent on which weight we choose. And this is like quite interesting because, of course, like we have to take like nice functions, so path monotone functions or something like this. And then like it seems that even when these functions are very different but share some kind of property, then the center is not influenced by choosing one or another. Of course, like this is not formal.
So there could be lots of pathological counterexamples.
Yeah, of course. Yes. Yeah, you can think about a tree or like a general graph, and you can always define a function mu such that the center is like the support of the center is the whole vertex set. So there will always be pathological cases. Yeah. But whenever you add some structure to mu, then like intuitively it seems that the center is not very dependent on which weight you give.
Any other questions? Let's thank our speaker again.